Well, hello and welcome YouTube. Mr. Robinson back here with yet another brand new exciting video, all math-based of course, and as always, it is an honor and a privilege to be serving you here today, as it is every day here in my virtual classroom. And welcome as you step on inside to the world of geometry here in Integrated Math 1. We begin with Chapter 8. I actually don't know the chapter name. It's probably Introduction to Geometry. Intro Geometric Concepts. And our first three we're going to learn here are on points, lines, and planes. All three of those, and I see them on the screen right now, what we're going to be talking about in just a second here. We're going to define them, we're going to be able to name them in figures and understand them. A lot less math-based thing, like, we're not mathing here as much as we're, like, defining things, and we have, like, 60 plus problems worth of doing things like that. So, this should come pretty, well, I shouldn't say easy. If you haven't learned it, you're learning it for the first time, there's that, but hopefully these intro things are just exactly that. They feel like introductions to things, and you're not doing a lot with them in general right now. Anyway, we're going to do the problem set in a moment. We're going to begin with the lecture portion, though. If you'd like to find anything specific, you can jump to the description section down below. I'll have a PDF attached of this actual set, as well as timestamps for where each individual problem is located. Without further ado, guys, I'm going to go ahead and get started. We're going to learn how to name points, lines, and planes. And when I say name them, I mean there is a universally accepted way in the world of geometry how we do it. It is a very specific thing to do. Okay, so that's the naming convention that we're going to figure out. Naming segments and rays, these are versions, kind of variations of lines within sketch intersections of lines and planes. Maybe, I don't know, get your rulers ready for lines, I suppose. And solve real-life problems involving lines and planes. Real life problem, you're having trouble with your significant other and you gotta, get in line to go on a plane. I don't know. I'm making stuff up. Anyway, a lot of new words here, right? I'm not going to say them all out loud right now. We're going to run into them at some point. Some of them you may already know, and you may think you know what a line is, but you may not fully understand it by definition, and you might not know how to name them yet. So, same with point, right? Okay. Let's begin with using undefined terms. So the words point, line, and plane are known as undefined terms because they do not have formal definitions, but there's an agreement about what they mean. So that's what I'm saying here, is that, they don't have formal definitions per se, but we're going to kind of give them that universal version of what we say about them. A point, it has no dimension. A dot represents a point. So you can draw a dot very thick or very thin, but we are just referencing that as just that single item that we're talking about. No dimension because there's nothing that it spans outward from in any such way. It's just that one point. Now, you're going to see the ways that some things are labeled beforehand. I don't know if this is me naming them right now with you, but there's an A above that point, so we're calling this point A, and that's just how we're going to name points. Now, points can exist on other things, such as lines here. You can see this point A and this point B on line L. A line is one dimension. Just can span this way, that way, or this way, that way. Just two directions, one dimension. It is represented by a line with two arrowheads, but it extends without end. So lines by definition, guys, they are infinite in length. They are not finite. There are other names for the ones that are finite or that have endpoints on either end. So these extend without end, that's what the arrows are indicating. Through any 2 points, there is exactly one line. You can use any 2 points on a line to name it. And you will only use 2 points on a line to name it. Not any 2 specific points, but you won't use more than 2 in a single name. So this line can be called a few things here. And this is where, this is your first time learning it. This is what we need to recognize. We can call this line L if they have it labeled as such. Generally, they will use a line, like a line M, line N, line P, and things like that. They'll do that lowercase if they just give it its general name. Otherwise, any points that are on the line, you can use any 2 of them because any 2 of them will represent that unique line only. I could call this line AB or line BA, and it's still that name. So you can either give it the name by saying the word line in front of it, or you can use this syntax right here. And what they did was they gave the letters A and B and drew the thing that kind of looks like a line with it, specifically with the arrows above it. So this is another way of saying line AB. We're going to be doing this a lot. This is another way of saying line BA. In fact, I'm going to do this significantly more than that one. If you don't put the letters above it, and we're going to talk about these, this represents the length of a segment AB. And so, there are a lot of things there that you have to be very specific about what you do, and that's how we do it in geometry. Let's talk about a plane. A plane is 2 dimensions, so as it spans this way, that way, it can also span this way, that way. Okay. It is represented by a shape that looks like a floor or a wall or a desk or something, but it extends without end. So planes aren't going to have the arrows drawn on them. I always had trouble, not myself, but like in teaching it, I always have trouble kind of getting people to understand that concept that the plane keeps going forever. So although I say a desk or something like that, a desk ends eventually, right? But you think of it like a flat surface. So a floor, a wall, but one that just goes forever. If my floor just went forever, boom, like the earth or whatever. And that's representing a plane. Okay, so 2-dimensional. Now, this is drawn in 3D space, so you're pretending like this thing is kind of, on that flat surface with that angle. That's what we're seeing there. And these are 3 points on the plane, ABC. This M doesn't have a point indicated with it, so they are labeling the plane as plane M, and that's what you can see right here. Let me read a few more things just to make sure that I cover it all. Through any 3 points not on the same line, there's exactly one plane. You can use 3 points. You can use 3 points that are not all on the same line to name a plane. So what they're saying is you don't want to use 3 collinear, and in fact, that's a word that's being used next. You don't want to use 3 points that are on the same line to name the plane, because otherwise that could be confused for something representing a line or what have you, or there's no actual dimensionality. That second dimension has not yet been explored. If these are just 3 points that go boop, 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 right that, where's the other dimension spanning from? Is it out this way or out this way or what? So you need them to be in different places like that. Now you can use 4 points on the plane to name it. I can put another point on here and call it point D, and this can be called plane ABCD or something like that. That's fine. But not through any 4 points are you always going to be able to draw one unique one plane. Okay, so generally, although we could probably name this plane BAC, plane CAB, things like that, you can reorder it. In this case here, it becomes redundant to get all the 6 different variations you can do. Call it ABC if you can, make it alphabetical. They're going to sometimes get clever with their names. They can call it, I don't know. Sometimes they spell things, basically, like that. So collinear points are points that lie on the same line. Coplanar points are points that lie in the same plane. A, B, and C are said to be coplanar. And A and B, well, any 2 points are collinear. But when you find 3 collinear points, like in this example, we can talk about it. Okay, so here are some examples, and we're going to go with the ones that they have answers for. Here we go. Give 2 other names for line PQ and for plane R. So let's do one at a time. Line PQ is the one line that is drawn through the points P and Q right here. So the other 2 names I can give it, and I'm not looking at the answers, I'm looking at you. The other 2 names I can give it, I can swap PQ and call it line QP. And there's also this N right here that's labeled with it, so we can also call it line N. We wouldn't call it line NQ or NP or anything like that. N is actually the name of it. So that should be these answers here. Where are we? Give 2 other names right here. Other names are QP and line N. So plane R. R, once again, is kind of the name designated for the plane itself, as it doesn't have a point really with it. So what we have to do is find other points that are on this plane. Now Q is clearly a point. If you can tell, again, this is kind of a 3D aspect of it. This line is like striking through the plane. It's kind of like my pen going through my hand right here. This is like that line going through that. The rest of the points look to be on the plane, including this line looks to be on the plane. So points that are coplanar are V, S, P, and T. Q is not on the plane. R is not a point, right? So I can name, let's see, give 2 other names for plane R. I can give any 3 letters that are on the plane. I could call it plane VSP. I could call it plane PSV. I just said go alphabetical, and suddenly one version I didn't. TPS. Oh, those are collinear though, so you don't want to do that. TPV, VPT, TSV, VST, VTS, things like that, right? So which ones did they give? And by the way, generally just try and use 3 letters. I said you could use 4, but try and use 3. Points SP and T lie in the same plane, so you can say SP, or on the same line, so you don't want to say that. Oh, where is it? Oh, SVT and PTV. SVT and PTV is what they said. Okay, what was the other question? Name 3 points that are collinear. Name 4 points that are coplanar. So the 3 points that are collinear, I did say, and they just said are S, P, and T. 4 points that are coplanar, I said that before, V, S, P, and T. And that's what they said on those. Okay. Using defined terms. Now, defined terms are ones that are clear to everyone what they're supposed to represent. Terms that can be described using known words such as point and line are called defined terms. So now we can use those in definitions for other things. Defined terms are like segment and ray. The definitions below use line AB and points A and B. So here's that line. It goes forever, and it goes through the points. Now, a segment is sometimes what people misconstrue as a line. A segment has 2 endpoints, endpoint, endpoint. That is also known as a line segment, because there are other versions of segments. You can have ones that curve from arcs and things like that. But they have 2 endpoints. Therefore, they have finite length. They don't go on forever. You can actually provide how long they are. The line segment AB, or segment AB, written as this. Notice the difference between this one and this one here. This one just looks like it has a segment bar. This one looks like it has a line bar. Okay, that makes sense. So no arrows on these ones. Consists of the endpoints A and B, and all points on line AB that are between A and B. Note that segment AB can also be named segment BA. So once again, you can reverse the order, and that's all good. Doesn't matter. Remember, these things can also be drawn up and down or diagonally. They don't have to be drawn left and right for these things to do what they are. Also, we're probably going to be looking at 3D figures a little more so. Points don't always, again, have to be drawn with that whole big point aspect. Eventually, we're going to see like a parallelogram, and it says A, B, C, and D. Well, this is a segment right here, A to B. I don't need big points on them to actually make that so. That's all I want to say for that. They didn't really talk about lengths, but again, segments have finite length, whereas lines do not. They're infinite. Rays. A ray is kind of the hybrid between a line and a segment. It has one endpoint, and then it extends infinitely in the other direction. So it has infinite length like a line, although line is more infinite because it goes in both directions, I guess. Now notice that a ray can go from an endpoint and out through another point. When we name it, this would be called ray AB. It would specifically start with, why'd that marker change? It would specifically start with the letter that represents the endpoint and then goes through another point afterward. Now, this one would be called ray BA specifically because B is the endpoint on this one and it goes through A and infinitely that way. Notice how the way that they're written right here, first of all, as they said, they are different rays. But notice how they're written. It's not like because this one goes to the left, we're going to call it AB and the arrow is going to go this way. This arrow on this writing is always going to go to the right. Once again, I want to make mention that it's not about which direction the rays are drawn, because again, it can be drawn up and down and diagonal as well. It's about which is the end point. And the end point always goes first, and the arrow always goes in this direction. Rays, once again, have infinite length. Opposite rays. If point C lies on line AB between A and B, then CA and CB are opposite rays. So basically, all 3 of these are collinear. What you start talking about opposite rays when you do things regarding angle measurements and stuff, they start talking about them because they talk about that being a point of intersection in the middle. But they're all collinear. C is in the middle. And there are a lot of ways that we can name. Here's a segment AC. I'm probably jumping the gun. But here's a segment AC. Here's a segment CB. Here's a segment AB. Things like that. There are a bunch of rays within here. That's the kind of questions they're going to be asking us to do. These aren't really math-based things, but understanding the definitions and how to name them. Okay, segments and rays are collinear when they lie on the same line. So opposite rays are collinear. That's what I was saying. Lines, segments, and rays are coplanar when they lie in the same plane. So the same thing, it's not just points that are said to be these things. It's also segments and rays and lines in some cases. Okay. Give another name for segment GH. So segment GH is right here. Notice that I did say segment because there's a bar above it, so we can only name it with those 2 endpoints. We cannot include other points within it, only those 2 letters. So the only other option here is segment HG, and that's what they're probably going to do right there. Boom. Segment HG. Notice the bar above. Must draw that. Part B, name all rays with endpoint J. Which of these rays are opposite rays? Now, again, when we say endpoint, you might think of it more like a start point, right? So starting from J, boom, we can go out there. JG, ray JG, ray JF, ray JH, ray JE. And those specifically, here's where they named them. Boom, boom, boom. Notice how J is the first one written. It's the endpoint, and it goes through the other points. Notice the arrow. Opposite rays, JE and JF are opposite rays. JH and JG are opposite rays. So they say JE and JF, JG and JH. Boom. Okay, let's skip monitoring progress. Sketching intersections. Two or more, and this is where if I have to draw some of these, I'm going to have trouble giving a version to you that makes sense. And I only hope that you can make sense of the ones that you see here. Two or more geometric figures intersect when they have one or more points in common. The intersection of the figures in the set of points of figures. I can't read. The intersection of the figures is the set of points the figures have in common. Some examples of intersections are shown below. Line M and N intersect at point A. Plane, they don't have the names of the planes, but this plane going up and down and this plane going left and right intersect at line Q. Planes intersect to form a line, lines intersect to form a point in that way. Now, they're going to talk about how to sketch them. I guess we're going to have to do some sketches. So just kind of get ready for that. I'm probably not going to... Oh, I thought they were teaching you how to do it. Okay, sketch a plane and a line that's in the plane. Boom, so here's that plane there. Boom, and draw on that line. Sketch a plane and a line that's not interplane. It does not intersect the plane. If it doesn't intersect the plane, it must be parallel to it. If it goes any other direction, even if I draw it like this and say, look, it's not intersecting, if that arrow thing is drawn in that way, the inference is it's going to go through there and strike through it, boom, and out the other side like that. So, because they go forever, right, as long as it's a line. Sketch a plane and a line that intersects the plane at a point. So a line can go through, strike through it, boom, and it just hits that one point and goes out. Sketching intersections of planes. So this is where they're showing some steps here, drawing vertical, and they said a second plane's horizontal, but again, it's that 3D kind of look. And hopefully you know what I mean by that. This isn't so much a parallelogram as it's like a flattened square, but we're looking at it from a perspective. And then we can draw a line through those that make that. I don't know how well I'm going to be able to draw them with the tools that I have, or making it make sense to you, but I'll do the best I can with it. Now, you show the intersection of the points of the planes on the end by drawing a line with that, and that helps give the perspective that you have, as well as the dotted lines that go in the background there. So that's going to be another helpful bit. Dashed lines. Okay. Solving real-life problems, modeling with mathematics. Here we go. The diagram shows a molecule of sulfur hexafluoride, the most potent greenhouse gas in the world. Did not know that. Name two different planes that contain line R. So line R is right here. Now planes that contain the line, you have to remember that planes are the two-dimensional thing. So for example, this plane here made up of this line and say that line. Boom, there's a plane. Line R can also have the plane that kind of has this line, this vertical line along with that line. So those kinds of planes there. So name two different planes. In the first one, let's move this vertical-ish plane out of the way. In the first one, I got to name three non-collinear points, like G, B, and F, for example. G, B, F can make a plane in that plane. For this other one, boom, like this. Again, containing line R, there it goes through. I can say A, B, and F. Okay, A, B, and F, for example, they are non-collinear and they go through there. So hopefully it makes sense what I'm talking about. Like that line P is now on this plane with this line R, whereas in the other one it was line Q with line R. I probably didn't draw it best, but that's the idea that I was going with. That might look a little better for you. So that's what we're doing with them. Now they might give different letters, and they're saying some things here. To solve the problem, you want to find points that are not collinear with each other, and so you need to name some things. So they said plane DEF contains line R. Here's D, E, F. These are non-collinear points that are like from this plane. And then they said plane CDF. CDF, those three right there. I said like CBF or something like that. Those three are non-collinear and they make this plane here, the vertical one. Okay, Okay, that's it for that portion, guys. We're going to now start with the vocabulary and core concept check. I mean, this whole thing's going to be vocabulary in the end, right? And core concept checking. But let's take a look at these. Compare collinear points and coplanar points. Well, collinear points are points that lie on the same line. Coplanar points are points that lie in the same plane. That's it. Which one doesn't belong? Which term doesn't belong with the other three? Number 2, explain your reasoning. This is segment AB. This is plane CDE. This is line FG. And this is ray HI. There are a couple things I could state that might differentiate among these. The letters don't relate, but I'm calling these A's and this a B. If there are 2 things that I can name that are different among them, for one, all 3 of these are using just the letter designations with the symbol as opposed to the word. And for another, these are drawn in one dimension. These are drawn in one dimension, whereas a plane is a 2-dimensional concept. So those are 2 different things that are kind of being mentioned there. CDE, I don't believe it's required, and you know what? That might be the difference, the second part, because there isn't a way to use a symbol to represent plane. If this wasn't here, I would believe that we'd be referring to this as a plane without saying the word plane. Okay? Because otherwise, if we're talking about a triangle, we're going to put a triangle symbol or say the word triangle or whatever. That being said, or a major arc, I believe they're called. That being said, these ones did not use the words, and they had an option to either use the words or the thing. So they could erase that word plane, and I think I'm still good on referring to it as a plane. Anyway, I would say that the reason those are different is because lines, rays, and segments are one-dimensional concepts, whereas planes are 2-dimensional concepts. Now, I might accidentally, and I apologize if I do this, sometimes I'm calling lines, rays, and segments 2-dimensional because I'm thinking that they're drawn within a 2-dimensional place. Like, you can draw lines on a plane, like on a piece of paper. Planes I think of in 3D space, like a piece of paper in the world. Things like that. So sorry if I ever accidentally call planes 3-dimensional and the lines 2-dimensional. I'm thinking about the space that they exist in to me. All right, guys, I'm going to go ahead and start this, the rest of this. Numbers 3 through 64 we have. I think a lot of these will be fast, but once I realize that we have to do some things with drawings, I'm not so sure. So, but you know what? Let's go ahead and take a look and see what we have. Oh, I didn't switch this slide here. Here we go. Boom. Okay, in exercises 3 to 6, we're going to use this diagram, and I'll probably keep it here and point to them. They want us to name 4 points. Anything that's not the letter S or T that are the names of the planes can represent the points on here. So I can name the letters A, B, C, and D, and those are fine. I'm leaving out E, but I can use it. And there's number 3. Perfect. Number 4, name 2 lines. I only see 2 lines on here that we can give a name designation to, because other ones that aren't drawn, the planes intersect at a line, but I don't have another letter for it. So we're talking about this line and this line. Now there's more than one way to name these 2 lines. The first one on top I can call line BC or line CB. But make sure you give the line symbol there, which has the 2 arrows above the bar. And then there's line DE, which I can also call line ED. But there it is. Number 5, name the plane that contains points A, B, and C. Well, you could call it plane ABC, but I think the general gist is they want you to know that it's this one that's kind of upright. And there's also a letter here associated with it, which is S. So I'm going to write plane S. I just came off saying that you probably don't have to use the word plane if you use 3 letters. This is just one single letter there. I really want to do it there. Number 6, name the plane that contains points A, D, and E. Notice that A is existing on 2 different planes that are drawn, but D and E are specifically on the plane right here that's a little flatter looking. And this T, not a point, is the name of that plane as well. So I'll be calling this one plane T. Okay, in exercises 7 through 10, use this diagram. Wacky, right? So what I see here is a plane. I see this line that's on the plane and this line that's striking through the plane at one point. These lines also are intersecting together at this point here. So we'll see how many of those things are giveaways of what we need to do. Give two other names for line WQ. Now W and Q is this line right here because those 2 points are on it. There are only two other names I can give based on their labels. One is flipping those letters and calling it line QW. The other is giving the name that they kind of give for the line itself, which is just G. That lowercase one is not a point. It is a name for the line. So line G. I think anytime you're using the single letter, see, I wouldn't call this G like this. That's not a proper designation, at least for geometric acceptance. We actually have to kind of say the word line with that thing to do it. Whereas this one, you can do either. Write the word line or give this above it. Those are the tricky parts where you might understand what I'm doing when I do it, and it's going to take some time for you to be able to do that on your own, you know? Number 8, give another name for plane V. Where's the V? Oh, I didn't see that. So plane V. So we have to name 3 points that are on the plane, but they should not be collinear. They mustn't be collinear. So I could not name it RQS or any version with these 3 letters only. W is not a point that's on the plane, so we have to use another set of 3 letters. And you could use 4. You could use 4, but I could call this plane RTS, for example, because they're non-collinear, or QST or something. They said give another name, so I'll just call it plane QST. And like I said, I don't know if it's required to actually use that word plane there, but to not confuse you for now, let's go ahead and do that. So QST. That one's pretty open-ended with a few options. Number 9, name 3 points that are collinear. Then name a 4th point that is not collinear with these 3 points. Well, I just mentioned how RQS are collinear, so I'll go ahead and say those. Points R, Q, and S are collinear. Another point that's not collinear with those is another point that is not sharing that line with them. So I could either say W or T. Either. So name a 4th point that is not collinear. W is not collinear. It's also not coplanar. Oh, actually take it back. W would be coplanar with these. We just don't have the plane that's drawn that represents it. But it's not collinear with R, Q, and S. Number 10, name a point that is not coplanar with R, S, and T. Oh, W. So let's change this one from W to T just to kind of have different answers. T is not collinear with them. And then on number 10, I want to say that W is not coplanar. Here's the thing. W is coplanar with them. It's just not on the plane that's drawn. I think I already said that out loud. But W is not coplanar with R, Q. Oh, R, S, and T. Oh, okay. There you go. I was going to say this book is having trouble with me. So R, S, and T. So I thought they were saying with the other 3 points. Yes, W is coplanar with R, Q, and S. We just don't see the plane that's drawn. R, S, and T, however, all exist on this unique plane. W is not on it. Okay. Let me get a sip of water here. Okay, we're going to use the diagram to answer exercises 11 through 16. Now, what we see, we don't see a plane drawn. That doesn't mean that these 2 lines aren't all on a plane together, which they are. These are lines that intersect at point E. Notice that E doesn't actually have a little point thing drawn on it. That is not required. But E is that point of the intersection among these lines here. So what is another name for segment BD? And I did say segment. Segment BD is this line segment right here that has this specific length. Boom, boom. The only other name I can give it is segment DB. I cannot give it anything with the letter E, only because this has these specific endpoints. Segments must be named by its endpoints only. Number 12. What is another name for segment AC? In the same vein, AC goes literally from A to C only. E is in the middle, but to name a segment, we only use 2 letters, only the endpoints, so I can only call it segment CA. Number 13. What is another name for ray AE? Now this one here, here's what ray AE is. Give me a second. I'm going to change this color and do something. Here's ray AE. A is the endpoint. It goes through E and it goes forever in this direction. It's that green arrowed thing. However, notice that A is, once again, an endpoint. It doesn't have an arrow. It begins here It goes through here and continues collinearly with C. It goes through C, and that's important. That's what we're going to talk about. And it goes forever that direction. So what's another name for ray AE? I need A to still be the endpoint, but it also goes through C. Therefore, I can call it ray AC as well. I can do ray AE or ray AC. There's no other name I can give it because A must be the endpoint if we're talking about that specific ray. Number 14, name all rays with endpoint E. They're all the ones that go outward from it. So ray EB, ray EC, ray ED, and ray EA. Of course, I'll go as alphabetically as I can. E has to be the first letter, but I mean, I'm going to start with EA. EA. Ray EA, ray EB, ray EC, oopsie, and ray ED. And I know they were referring to opposite rays before, so we do have opposite. Actually, that might be a question on here, so before I keep talking. So there's that. Name two. Oh, here we go. Number 15. Name two pairs of opposite rays. So opposite rays are ones that they're opposite each other. EB and ED are opposite rays. They are collinear. Together they form a line like that. They're in exact opposite directions. So ray EB and ray ED are opposite rays. Opposite rays. Ray EB and ray ED. And also ray EA and ray EC. I just got a comment on one of my things. 34 is a lot of problems. Try searching up math rule 34. I don't know what that video, I got a pop-up on my computer that says that. I got to see what comment and what video that's in. Give me 1 second. I'm really curious about this. I know I'm hijacking my own video with this thing. What are they talking about? 34 is a lot of problems. Oh, it's a 34 problem review. Anyway, whatever. It might be a bot that said that. Okay. Is that it? Yeah. Okay. Number 16. Name one pair of rays that are not opposite rays. Well, we named the pairs of opposite rays. Here's a set, EA and EB. They're not opposite rays. They share the same endpoint. That doesn't mean they are opposite rays. My neck is really bothering me here. Not op rays. Oppenheimer. EA and EB. Now, here are also non-opposite rays. AC and, BD, right? If I go and do this, these are not opposite rays either, okay? I think they're kind of talking about ones that share the same endpoint, though. So you can make sure that you aren't confusing yourself with what does work and what doesn't. Number 17 and 24. Okay, here's where we have to do some sketches. Sketch the figure described. Now, my drawings are probably not going to come out very good when it comes to giving you that depth perception, but really try and make everything as 3D sounding as it is. Now, I do have some tools that I can use, like the line tool and stuff, and I might use it. Sketch the figure. We have plane P and line L intersecting at one point. So here's an example of plane P. I have to label it, so I'm going to put it in the corner there. Line L. Here's line L. It's going at that point right there into the plane, and on the back end, on the bottom, I have that there extending on the other side. This is what I'm going to call line L. Actually, that looks good. I'm very proud of that drawing, and I hope you can make sense of what this is. It's like this punching through that paper, coming out the other side. The dashed line is just a version of going behind the plane. We have a lot of things we have to draw, though, here. Number 18. Plane K and line M intersecting at all points on line M. Line M intersecting at all points on line M. Did they mean on all points on plane K? Intersecting at all points on line M. I think they mean, oh boy, I'm sorry if I'm going to do this wrong. I don't know if I'm reading this wrong or what. Here's plane K, and here's a line that's on the plane. I don't know if that's what they mean. Line M intersecting at all points on line M. I don't know, guys. That's what I'm going to draw. I'm sorry if I'm doing that wrong. I think this should be saying line M intersecting at all points on plane K. That way, we're basically saying that the line is on the plane. And that's what I'm going with there. I'm sorry if that's wrong, if I'm misreading what that is. I really do apologize. Number 19. Ray AB and ray AC. Draw them. Well, the idea of drawing these, and we're assuming A is the same endpoint, like it's part of the same figure. So if this is A, it's an endpoint, and it goes through, here's a ray that goes through B there, and from A, here can be another one that goes through C like that. These are two different rays, AB and AC. Oh, line AC. I missed that. And you know what? I probably should be labeling some of these here. Okay, for line AC, let me move this A letter here. Give me one moment. I thought they were just rays. I'm going to extend this through like this. So, there we go. So, line AC, here's a line defined by the arrows and 2 points that go through that line that are like that. Here's ray AB like that. All right. Number 20. Now I got to see these specifically. Ray MN and line NX. So with this one, I can do the same kind of version of this first drawing here. Ray MN. Only this time, N is the one that contains the line. So line NX, I would do something like this, where X is a point on this line that goes through N instead of through M. But M is the endpoint containing the ray, or for the ray. Well, these drawings are okay for me to do. It's probably those other 3D ones that would look weird. Number 21, plane M and NB, ray NB intersecting at B. So I guess the way they're describing that, maybe this other one wasn't a typo. You know what? I'm going to erase that in case I'm looking foolish when I'm saying that. I think what they're saying... I think what they're saying is these two are intersecting at all points on line M. Now, so I think what I drew was correct on this one, number 18. Number 21 is saying these two things are intersecting at point B. So that means that point B is on the plane. And that's how I interpreted it the first time. I didn't realize that they were saying, I thought they were saying, draw plane M and then draw ray NB intersecting at B. And I said, what are you talking about? These two are intersecting there. It makes a lot more sense. I don't know if like a comma would help in these instances here. It's just to, you know, take out ambiguity. Okay. Plane M and ray NB. Now, I'm going to draw N up here, the endpoint for the ray. It's going to go through. It's going to hit B right here. Boom. But it is a ray, so it's got to extend out the other side, say like that. Boom. And there it is. B is on the plane. We intersect at B with that plane, and it is a ray starting with N. Okay. Pardon the confusion. This is me looking at it for the first time. Number 22. We have plane M and ray NB, but they're intersecting at A. So this time, literally, I can do this same drawing, but I got to change B. B has to be somewhere on this ray, not on the plane. That is reserved for the letter A. So N, B, and A will all be collinear, but B has to be somewhere on this ray that is not that point of intersection. It can be above it. It could have been below it over here. Any of those would have worked like that. Number 23, draw plane A and plane B not intersecting. For planes to not intersect, I think of this as an absolute must. They must be parallel. So how's the best way for me to draw two parallel planes? Copy paste. Here are two planes that are not intersecting for myself right here. Plane A and plane B not intersecting. Boom. Number 24 says draw planes C and D intersecting at line XY. This is ones where, and you can draw them how you'd like as long as it looks like they're going to intersect in some way. Now, this is one where I want to give it that good 3D look as well, so you have to pardon me as I do some of this. I'm going to draw a plane that kind of looks like this. It's kind of like a ramp piece. And then another one's kind of coming out of it. I'm going to have to do some dotted line stuff here in a bit. Dashed line stuff. So you see how those are kind of intersecting like that? Now what I'll probably need to do is dash this one up a little bit here. And I think that's it. Now the intersection of those two planes is going to be this line that goes like, say, from there to there. Oh, okay. Well, that's a little awkwardly drawn. Let me try and fix that then. There we go. All right. So I'm going to have them boom like that. Now they're intersecting at this line XY. And to make it a line, you probably want to extend this farther. So boom. This is line XY. As best I can do with that. This is going to be plane C and plane D like that. Boom. So that can get a little confusing, especially when I don't know. It can look a little confusing when I constructed it. But that plane with that plane intersecting at that line. Okay, error analysis. In exercises 25 and 26, describe and correct the error in naming opposite rays in the diagram. Ray AD and ray AC are opposite rays. Well, here's the problem. They're not. Here's ray AD, and that's very much a ray, and here's ray AC. They share the same endpoint. That doesn't make them opposite rays. Now they said, correct it. That must mean we have to kind of say something that does make opposite rays, right? So for number 25, now my problem with geometry, now that I'm remembering, now that I'm going to do this, I'm going to type some stuff out, but I can't put the symbols above, so I have to put them in after. So it's kind of, you have to be patient with me on that. AD and AC may share the same endpoint, but they are not opposite rays because not all 3 points are collinear and going opposite directions. Now, you do have to say the going opposite directions part, because here's another version of me saying, hey, these are collinear, why aren't these opposite rays? Here's AC and AD. Ray AC, ray AD. Well, they're literally the same ray. They do have to go opposite directions to become that, so you couldn't say that. So what's a pair of opposite rays? Let's do AD and AB. Ray AD and ray AB are opposite rays. So you can do that. Now, I haven't yet drawn the ray symbol, so I got to do that here. Ray, 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 ray. Number 26, YC and YE are opposite rays. The problem is not that they wouldn't be opposite rays. Look at the symbol that they used. They used a segment bar instead on number 26. So the idea is right. Y is an endpoint, and these are opposite directions, collinear, all that kind of stuff, right? Problem is they used a segment bar. So the segment bar was used instead of the ray bar. It should say YC and YE, and then let me put the ray bar above it. I'm surprised they didn't do one where they made the ray bar go the other way. That would have been a classic case of doing something where the endpoint was the last letter instead of the first one. You know, those are probably more common mistakes. I don't think people are going to see things that are not opposite rays and call them opposite rays as much. All right, numbers 27 to 34, use the diagram. So we kind of have a cube-looking thing. This is one of our 3D objects. Points I and J are not the only points on here, though. Every single one of these represents a point. These are the only ones that are just not on vertices. A is a vertex of all three of these things meeting together here, right? So that's going to be just something to make sure you understand. Those are still points. So number 27. Name a point that is collinear with points E and H. On this line shared with E and H is point J. So that is number 27, point J. Number 28, name a point that is collinear with points B and I. So on this part with B and I exists C. So point C is collinear with that. Normally, I'm a lot more descriptive with what I do here. Point C is collinear with whatever. No, not right now. Number 29, name a point that is not collinear with points E and H. As long as you don't say J or E and H, as long as you don't say any of these three letters, you're good. Open-ended. A, B, C, D, F, G, or I. Let's say I. Point I. Why not? Number 30, name a point that is not collinear with points B and I. Once again, as long as you don't say the letters B, I, or C, you're good. I'm going to say point D. Number 31, name a point that is coplanar with points D, A, and B. What's nice about something like this is I can even identify that plane for you because it's kind of drawn. Here's the points D, A, and B. It's this top-facing plane that we're talking about. So coplanar are any other points that exist on this plane. Options for us are I or C. I'm going to go ahead and say point C is coplanar with them. Number 32, name a point that is coplanar with points C, G, and F. C, G, and F is the back facing right here. Now D is not, so hopefully you understand, it's this back one, right? Boom. D is not on that plane. D is this like front facing one right there. The only other ones that are coplanar with it are letters I and F. So I'm going to go ahead and say point, wait, F is one of them, huh? C, G, and F. B, either B and I. I'm going to go ahead and say point B here. Hopefully I get to use different letters for all of these. I didn't really see what the other ones were yet, but hopefully I get to. Number 33, name the intersection of plane AEH and plane FBE. Plane AEH is the front-facing one. I'll just draw the outline. Plane FBE is this one on the left side, this left-facing one. And we have to name the intersection of the plane, of the two planes. These two planes are intersecting at this segment. I don't know if they're going to call it a segment or a line. Right? I'm kind of in between whether we'd call it that. I believe because they're calling these planes that they'd be going on forever. So AE is more than just a segment. It is a line that happens to hit those points. So I'm going to call it line AE. So when I say it's a cube looking thing, it's not exactly really a cube. It's just four planes that intersect with the appearance of a cube. Oh, there's still another question. Number 34. Name the intersection of plane BGF and plane HDG. So the same thing, it's going to be a line as long as they do intersect. Plane BGF right here represents this plane. And again, it's more than just that, but I'm just drawing that. Plane HDG is, here's D, here's H, here's G. So it looks like this line CG or GC right here is the intersection of those two planes there. So line CG. So good, I think every answer was unique here. Oh no, I did use point C twice. You know what? I didn't even notice that. Is there a way I can change one of those answers here? 31, name a point that is coplanar. 28, name a point that's collinear. Oh. D, A, and B. I could have said point I for that, but then it changes that answer. And I could change, I'm good. I tried to make them all different, but oh well. All right. Number 35 to 38, name the geometric term modeled by the object. What? I guess the whole dart looks like a ray. Oh, they're pointing at something here. Are they talking about this? That looks like a ray to me. They're pointing at the dart hitting that thing. I'm going to call number 35 a point. I thought they meant like, I don't know. I'm going to call it a point. Number 36. I guess they're representing the flat surface that is the screen for the television. So something that's resembling that of a plane. Flat surface. So number 36, I'm going to call plane. Number 37, it's that yo-yo string. Now, a yo-yo string, you have to be careful. Don't say line automatically. Lines extend infinitely. A string has finite length. So that's a word we haven't been saying too much here, but it is segment. That's a line segment in my head. That's what I'm thinking of when they're pointing at that. Now, number 38, they're pointing at, you can say they're pointing at the building. It looks like what they're specifically pointing at, see, they didn't point at anything on the screen. Looks like what they're specifically pointing at is where these lines intersect. This line intersecting with this line, intersecting with this line. They're intersecting at a point. I'm going to call number 38 a point, which was also the same as number 35, but it still is that to me. And in exercises 39 to 44, use the diagram to name all points that are not coplanar with the given points. Name all of the points that are not coplanar with the given points. They didn't say collinear, they said coplanar. So, N, K, and L are right here. Now, M shares the plane with the plane NKL, therefore M is coplanar with those 3 points. All the points that are not are the other ones, and I'm going to try and stay alphabetical. P, Q, R, S. P, Q, R, and S. You want to list them, commas and stuff like that. That's kind of what we're saying on it. Number 40, PQN. Identify which plane makes plane PQN. PQN is the front-facing one. M is coplanar with it. Once again, it shares it. So it's these 4 letters in the back. JKL. LKLRS. If I'm to be alphabetical. Number 41, PQ and R. I might not draw them each time here. I might. PQR is the bottom facing plane. S is coplanar with it, but these 4 are not. JKLMN. KLMN. Number 42, RK and N. Now, there are 6 different things, so I imagine we're going to do all 6 faces. That way, they're all different answers. RK and N is the left face, which Q is coplanar on, but not these 4. L, M, P, and S. Number 43. I like the questions are pretty fast. P, S, and K. Psk, psk. I guess use pst. P, S, and K. Oh, okay. You know what? This one's unique. So, P, S, and K, they didn't draw the plane. So I'm gonna kind of draw it for you. P, S, and K, boom, it's this plane here, which for all accounts, I'm going to say that N is on that plane as well. Can you kind of see how that's working? So these are coplanar with each other. R is not on that plane. R is in the back corner. R and Q are not on this plane. L and M are not, and M is also not. L and M are not in this plane. So I'm going to say L, M, Q, and R. Oh, I don't know my alphabet order. That's what I'm trying to write them in order, alphabetically. And I'm having troubles. R before Q. So I guess there's more than just the 6 outer facings that they're going to do. Probably this is more of the same. Q, K, and L. So here's Q to K. Here's K to L. So you can kind of imagine what this plane would be represented as if you do kind of like this right here. So P is also coplanar with them. But what is not are N and M and R and S. But if I'm going to alphabetical, M, N, R, S. M, N, R, S. So it's good that I drew those ones out. Sorry, that was 44 here. Boom. Okay, number 45 and 46 are critical thinking. 45 says, given 2 points on a line and a third point not on the line, is it possible to draw a plane that includes the line and the third point? Explain your reasoning. Yes. So I'm kind of drawing on the side here. Well, here's a line, 2 points on it, and here's the third point not on it. Any 3 non-collinear points make a plane. So it's always the case. Oh, and then I should just draw the plane. Boom, here's a plane with blah, blah, blah. So, yes, that's always going to be the case. Number 46. That was very critical. Is it possible for one point to be in 2 different planes? Explain your reasoning. Yeah, and I forget if it was in these problems or in the lecture portion that we saw it. The one with the A? This one. This point is in 2 different planes right here. So honestly, I'm just going to copy and paste this figure. So, I hope that's okay. A is an example of that on this one. Right here. Now, you do not have to just do. I don't think they ask you to draw examples, but you can describe them, I suppose. Yes, A is on two different planes here. I forget if that was actually a question at the time. What planes A on? Now you can draw any planes through any point. You can draw an infinite number of them. I can draw a bunch of. I can make up a bunch of other planes that go through A or for B, for that matter. But there's just a visual of showing that there. Pardon me. Number 47, reasoning. Explain why a four-legged chair may rock from side to side, even if the floor is level. Would a three-legged chair on the same level floor rock from side to side? Why or why not? No, it would not. I'm trying to imagine this way. I'm good. The two legs going that way, good. On this side, I go over, and I collapse because that fourth leg isn't there. How do we answer that, though? Hold on a second. Okay. May rock from side to side. I'm trying to see how they're like asking the question. Because I'm thinking more of like how the thing would collapse if I tried, versus the idea of the rocking aspect. I need to think in terms of geometry. So what are we seeing? With a level floor, I don't know how to answer what they're asking, and I feel bad for you guys about what they want me to say. I'm not going to demonstrate it. Explain why a four-legged chair may rock even if the floor is level. I'm having trouble kind of answering like that aspect. All I want to say is if I go on this side, the two legs keep me in balance, and on this side there's only one leg, and on a point I'm not in balance. And I don't really know if I'm answering that. Let me think about what they might want to say. Give me a second. Okay. I think I misunderstood the question. I thought they meant if I take my chair and tip it, you know what I mean? Where I actually tip legs up, because I'm a kid at heart. I do that all the time. Whee! And I go from side to side and lift two legs up here and two legs up here. I don't think that's what they're asking. I think that they're asking like that naturally. There's just a little bit of wiggle on the things there. That's what I think they're asking, why it may do some tipping. That makes a lot more sense with respect to geometry stuff. So why might a four-legged chair still do a little bit of unevenness? I think that's the way we should say that. It's not me being playful. It's just like, hey, this is a little wobbly. You know what I mean? Because any three non-collinear points will make a plane. They can always lie on that plane together, whatever they are. But that fourth leg, in conjunction with those other three on that plane, might not be that same length and on that plane with them. While 3 points, any three non-collinear points, and they are non-collinear for a chair, points are coplanar, the fourth point may not necessarily be the bottom of the leg, right? May not necessarily be on that plane. Like a longer leg, longer chair leg, something like that. Okay, that makes a lot more sense on that. Now, would a three-legged chair on the same level floor rock from side to side? Well, no, because they would all be on the same plane. A three-legged chair, this isn't about tipping over and stuff. I apologize, I was not thinking of this problem correctly. A three-legged chair would all be coplanar. It would always be on the same plane. Therefore, it wouldn't rock from side to side. They should have just spoken on unevenness, not rocking. When I hear rocking side to side, I'm thinking wee and doing things like that. Or backward and forward, which I would do a lot as well. All right, number 48, thought-provoking. That was thought-provoking on 47. You're designing the living room of an apartment. Counting the floor, walls, and ceiling, you want the design to contain at least 8 different planes. Draw a diagram of your design, label each plane in your design. So in a basic construction like the cube look of these ones right here, that's only 6 different planes, okay, in something like this. So what you have to do, I'm going to just copy and paste this one just to get kind of things started on the visual. Maybe I can do something off of that specifically. So I'm going to copy and paste this thing here. Just ignore the letters for a moment and all that. So this is 6 different facings, right? This is not 8. Counting the floor, walls, and ceiling, one design contain at least 8 different planes. So you need to angle something somewhere to make it different. Okay, so I'm going to take this design and start to do some construction with it. I'm going to just work around it like this, boom, boom, boom. But then I need to improvise a little bit. So here's what I'm going to do. I'm going to cut this one short instead, and I'm going to go upward like that, if that's okay. And I'm going to go like inward on this thing. Let's go like inward like this, and then meet it back out over here. You're going to see what this looks like when I remove the green one. To me, in my mind, this will give me something that's resembling of like more walls in the thing, in the apartment. I don't know what this apartment would actually be representing when it comes to that cutaway. It's just the angle of the building, say, and I want to get it on this side here so you can really see what I'm talking about. And I'll do some dotted lines for the rest of those other ones, dashed lines, I should say. Maybe even thin them out just a little bit here. Oh yeah, here we go. Hopefully this actually looks okay when I get rid of this. Okay, and I want to see if this is actually 8 planes or not. And I want to see if you can see this with me. There we go. So when I remove it, oh, I'm missing a thingy. So when I remove that, see what we're dealing with now, right? We have the top one. This is 2, 3, 4, 5, 6, 7. Maybe I should cut away somewhere else. The bottom is 7, right? So that's 7 planes. So, oh, I went from 6 to 7, right? I could have, let's just angle on the back. I mean, this is going to take some improvisation here, but I'm going to angle on this back wall right here like this. So now instead it's going to have, oh, quite a bit of things I have to change with that now. Quite a bit of things. So this is just going to be one interesting drawing here, right? But hey, I'm a designer, man. I'm an architect. I'm a what? Yeah, I'm a designer. I'm designing. So here's the 8th plane. Right here. This apartment is just not working here. So, kind of interesting. So in the back, 1, 2, 3 planes. The top is 4. And then 5, 6, 7, 8. Were there 8 before? 9. Wait a minute. Hold on. Did I not count this right before? Hold on, before I do too much. 1, 2, 1 on the left, 2 in the back, 3 on top, 4, 5, 6, 7, 8. Oh, there were 8 before. Oh, I apologize. I must have miscounted something or not counted something. I might not have counted the back wall before. Okay, here are 8 of them. My bad. Sorry about that. Label each plane in your design. Oh, wow. Okay, so A is the front. B is the left. C is the back. D is this one here. Here's E, here's F. G is on top. H is on bottom. Okay. I must have not counted the back or something. I was confused why there weren't 2 planes. I could have sworn that, hey, wait, these 2 are going to make up for it. Oh, okay. All right, that's 48, I guess. Number 49. Looking for structure. Indeed, I am. The two coplanar intersecting lines will always intersect at one point. Agreed. What is the greatest number of intersection points that exist if you draw 4 coplanar lines? Explain. What is the greatest number of intersection points if you draw 4 coplanar lines? So I'm going to draw myself a big old plane right here. how many times can these do at most? You just want to make sure they always intersect uniquely. Okay, so I'm going to draw lines all throughout. So these two are intersecting. So these are both on the plane. They're intersecting together. I want to make sure that another line intersects these two at different places, like that. And a fourth one, I need to make sure it intersects at as many as I can here. 1, 2, 3, boom. So I believe, if I did this right, this is 1, 2, 3, 4, 5, 6 different points of intersection there. Now they want me to explain it. I don't know. It's just the drawing. The first two intersected once. The next one intersected with the other two. The next one intersected with the other three. As long as you keep adding, I think drawing another one will add another 4 of them and make 10 intersection points. 1, 2, 3, 4 more ones. So that's just kind of the idea. So 6 total. The first two intersect at one point. The third intersects the other two at 2 different points. Here, I'll say 1 point, 2 different points. And the fourth one intersects, the fourth line intersects the other 3 at 3 different points. 1 plus 2 plus 3 equals 6. You just keep adding as long as you draw them right. As long as they don't intersect at the same points together. Whoops. And you visually get them to intersect together. Okay, number 50. How do you see it? You and your friend walk in opposite directions, forming opposite rays. That's what I always think when I do that. You were originally on the corner of Apple Avenue and Cherry Court. So we were originally right here. Part A, name 2 possibilities of the road and direction you and your friend may have traveled. To go opposite rays, we could have gone in opposite directions of Cherry Court or opposite directions of Apple Avenue. Boom, like that. So, number 50. My friend and I could have traveled on opposite directions. In opposite directions, not on. Cherry Court. Okay. It's part A. That's how I see it. Part B. You and your friend claims he went north on Cherry Court and you went east on Apple Avenue. Did he claim I did or did I do that? Make an argument as to why you know this could not have happened, because they're not opposite rays. Those are not opposite rays. North and east are not opposite directions. This is not possible, as north and east are not opposite directions. Better yet, hold on. Better yet, we didn't even travel on the same road. Now, I'm very aware of roads. I was literally just paying attention to this yesterday. I'm very aware of roads that change their street name as you cross the intersection. Maybe it's Cherry Court right here, or maybe Cherry Court right here, and then right here it's whatever, something else. You know what I mean? But there's that. I'm surprised it's called Cherry Court as well, given that I don't see a cul-de-sac there. It doesn't look very dead-endish, at least not yet. All right. Numbers 51 and 52, or from 51 to 54, graph the inequality on a number line. Okay. Tell whether the graph is a segment, a ray, or rays, a point, or a line. Okay, so there's some algebra tie-in here. So this is where I get to copy down the problem. X is less than or equal to 3. Now for me, when I draw these with you guys, you might remember, I'll place 0 on here. I'll place the boundary point there, the boundary value. X is less than or equal to 3 is looking like that. Now what is this? This is a ray. This is a ray. Endpoint on 3 and go into the left in that direction. All right, some algebra being used. Number 52 is a compound inequality. This is kind of cool that they're doing this. I like it. -7 is less than or equal to x, which is less than or equal to 4. X is between negative 7 and 4, including negative 7 and 4. So negative 7, 4, and 0 in between them. Close circles on these guys, and no arrows drawn, right? It's joining these two together right here for our x's. That is a segment. I'm very curious if they do anywhere it's not equal to, it's just less than, then it's an open circle. Then it's not an actual point on there. So I'm guessing they're not going to do that. Otherwise, they're going to trick me up with what the answer should be. I wouldn't know. Number 53. X is greater than or equal to 5. Or x is less than or equal to negative 2. This is often a case where these are split, and that's what you're going to see right here. Negative 2 and 5 with 0. I generally do 0 first. I haven't done them in a while. X is less than or equal to negative 2 is this way. X is greater than or equal to 5 is this way. That is rays. In a way, they're opposite rays. You know what I mean? Rays. And 54, absolute value of x is less than or equal to 0. Well, in terms of like maybe we'll solve that first to make sense of it, but it's one of those ones where we're saying either x is less than or equal to 0 or x is greater than or equal to negative 0. I guess that's the way that I'd say that. Wait a second. No, I'm sorry. No. Forget how I was saying that. Or the opposite of x is less than or equal to 0. Anyway, it's a way of saying that we have to be within 0 units of 0 in either direction, and this is as best as I can say. X I'm really having trouble saying what I want to say here. The only value of x that I could plug in here to stay within 0 units of 0, we need to stay within 0 units of 0 on this side and this side. There we go. Negative and positive 0. That's what I wanted to say. Not or, but and. Or, not or, but and. What's the only way that this is possible? It's if x equals 0. That was a trick within itself for me to say what I wanted to say, but that's how I got to say it. The only x that we can do is 0. Now, how do you do one value on a number line? You just draw a point. A point. We generally don't do that because that's just kind of a weird representation, but it is that. All right, number 55. Use the diagram. Looks like a tennis court, indoor tennis court. Name 2 points that are collinear with P. K and N. K and N are collinear with P. Number 56. Name 2 planes that contain J. Okay, I was looking for other labels with the letters. So J is part of this wall and part of the ceiling. The ceiling I can call plane JKL because they're non-collinear there. Plane JKL, or planes JKL and then this one here I could say like JKQ or JPQ or anything like that. Let's say JNQ. I don't know if we're going to use that letter N at all, so I'm going to do that. By the way, I don't have to use the letter J when I say that. It still has it on there. Oh, these are not different numbers. Hold on a second. That's part A, part B. Part C, name all the points that are in more than one plane. So any points that are on these lines, the lines are made up of multiple planes. I don't see one that's not because they're all on lines. So I'm going to name every point. JKL, MN, PQ. I'm going to do it alphabetically. JKL, I should just say all of them. M, N, P, and Q. All right, now we're on number 56. In exercises 56 to 63, complete the statement with always, sometimes, or never. Explain your reasoning. Okay, what I'm going to do is I'm just going to copy paste this whole set so I have it on this side. Oh, this might crash. Hold on. Oh, it just crashed. Give me one moment here, okay? Let me address that. Hold on. Okay, so I restored this. Well, I brought up this thing again. I lost all my work. I don't care because I don't go back and look at it. but just that's why this thing's wiped out, whatever. So, okay, I lost all this stuff. So if I have to recall other things, I can't. I'll have to redraw them. But when I was trying to copy this is what happens. This software crashes in and of itself sometimes when I do that. I don't know why. This is what I was trying to copy and paste over. Now I have to shrink it. So, whatever. Anyway, it's still on the video, right? Everything we did. So, that's cool. But I do sometimes like to get some archived things from before. All right. So, always, sometimes, or never. Number 56. Getting my pen stuff back. A line blank has endpoints. A line never has endpoints. Now, it says explain your reasoning. I'm going to do these things out loud. Lines go on forever. They extend infinitely in either direction there. Segments have endpoints. So array has one endpoint. Number 57. A line and a point blank intersect. I mean, sometimes. In the case of sometimes, I'd like to give examples where they do and where they don't. Here's a line and a point intersecting. Here's a line and a point not intersecting. 58. A line and a plane and a point blank intersect. So that's also sometimes for the same reason. Imagine the same drawings, but instead of lines, we have planes. So I have a plane and a point in it, and a plane and a point not on it. Two planes blank intersect in a line. If they intersect, it would be in a line. If they don't intersect, then there's no intersection. So that's also a sometimes. Because there are parallel planes. We even drew one. I would show you it, but I lost it. So you'll have to rewind and find that specific one. I'm not doing these. I'm sorry. Blank, blank, blank. All right. Number 60. 2 points blank determine a line. Well, two points themselves are just separate like that. But if you draw a line through them, basically you can draw a line through any 2 points, and those 2 points, it can only make one unique line. So I'm going to say always for that. The idea is those 2 points make the line. Number 61. Any 3 points blank determine a plane. I guess in that same way, we're just trying to come up with that. I'd say always, unless they're collinear. So sometimes. So understand, if they're collinear, then they don't determine a plane. Those still are just determining a line. Number 62. Any 3 points not on the same line blank determine a plane. So that's what we're saying, right? Any 3 points on 61 only determine a plane if not collinear. This is that not collinear, right? Not on the same line. So this one would be always. And then number 63. Oh, 64 is the last question. I didn't even think about that. I thought there were like 2 more pages to go. Number 63. 2 lines that are not parallel blank intersect. We didn't run across this yet, but you might be thinking, see, okay, this one's a little bit trickier for me to even talk about here. Parallel lines don't intersect, right? Here's parallel, here's parallel. But what if they're talking about lines that aren't parallel? You're thinking, well, if they're not parallel. See, some people will do this. They'll go like, Mr. Robinson, look, these aren't parallel. They don't intersect. And I'll say, well, yeah, they do. Because they're lines, they go forever. So eventually, they will intersect. But here's the tricky part. And I have no real good way of doing this outside of getting like one of those cube things again. Give me 1 second. Give me 1 second. Give me 1 second. Okay, let me borrow this one here. Okay. Actually, where's that green one? There's less markings. Here we go. There are lines on this very diagram that are not parallel. You might not know that they're not parallel. Just because they don't intersect doesn't mean they're parallel. But they won't intersect. For example, this line here, KL, and this line here, MP. Okay. Now you might say, oh, look, it's going to intersect here. No, no, no. Think of it like the cube that it is. These are not intersecting, right? This PM or MP is in front while the KL is in the back. You know what I mean? I can thin this one out and thicken this one out if that gives you the better just appearance of one of the other. I don't know. But one's in front, one's in back, right? They're not touching. It's like my arm here and my arm here. They're not touching, right? Those are not parallel lines. Now, they didn't use this word, and I don't believe it was one of the target words or whatever. But the word is skew. These lines are skew. So 2 lines that are not parallel, They'll sometimes intersect. But skew lines, SKEW, are an exception. Now, you need to have 3D space for this to happen. But that is what we're doing there. Oh, I'm not even on the right page anymore. But that's the idea. Okay? Okay. Number 64. Last question. Abstract reasoning. Is it possible for 3 planes to never intersect? Yeah, if they're parallel. Intersect in one line? Yes. Intersect in one point? Yes. Sketch the possible. Okay, so let me draw these. So number 64. Here are 3 planes that never intersect. I'm going to copy paste this. So So 1, 2, 3. Never intersect. Okay, the next one is not going to be a good looking drawing, all right? But intersect at one line. Let's say I have a plane that's going like this, a plane that's going the other direction. This is what's not going to look good. I'm not going to do the dotted line things very well here. Another plane that's going through here. Got that? And then a third one maybe going through the middle like that. These are all intersecting together at this line right here. Intersect at one line. They all have to kind of be in that same verticality or horizontality or whatever. They have to kind of have that to intersect at one line. Intersect at one point, you have to have them kind of all be in their own axes, like this axis, and this axis right here. So imagine one that's like full frontal, boom. One that's kind of like laid down right here, boom. And then a third one that's going kind of like this direction here, boom. Now all 3 of these, because here's the idea, right? They all have their sets of lines that intersect together. These 2 planes, this one and this one, intersect at this line. These 2 planes here, this one and this one, intersect at this line. And then these 2 planes here, this one and this one, intersect at this line here. So 3 lines are intersecting at one point. Boom, like that. So planes intersect at one point. All right, that's kind of what I'm going to do with that. That's abstract reasoning, yo. And that's it. And guys, that ought to do it for this one. This is Mr. Robinson. Thank you so much for watching. So listen, I don't think they covered everything in the lecture portion in the greatest of detail with the symbols and things. And they didn't talk too much about segments yet. I assume it's going in the next sections. I haven't read up on them to know what they're exactly covering, what we're covering in the chapter. It's Intro to Geometry. But that being said, I think when they talk about segments more, we're going to talk about the idea that they have finite length. I think, like that thing of skew lines and stuff. Okay, that's just a definition of things. So not everything is fully covered. But they didn't say things such as, we don't use 3 letters to name a line, segment, or array. Things like that. So I hope that the things I mentioned there do cover them. Little hiccups here and there, but I hope that was good enough for you guys. Thank you so much. That'll do it for this one. Take care. I'm going to see you in the next one.